Good morning, guys.
Morning.
Right. Okay. Caitlin,
Yes.
I just saw you had a question. Do you mind share with everybody so we can?
Yeah.
Okay.
So basically I was just wondering if there's an oblique incident, if we would have to be able to determine if there's a reflection. Like I know there are certain circumstances, but it's not as easy or as simple as the normal incidents because it's not like you can say, oh, there's two different impedances.
Okay. Okay, Maria, look. Let's try to get this straight out. Okay. Now let us just say that, okay, yes, this is our transducer. And let's say it's okay, we have a tissue boundary. Okay. And let's say it's okay. Yes, so we know what, yes, we have a tissue boundary here. Okay. Now, in this instance, we can say it's okay, we will have this is a normal incident. So that makes, okay, as a 90-degree angle. Did that make sense?
Yes.
Good. Now, if the impedance of one medium is not equal to the impedance of another medium, then we have a reflection.
Yeah.
Did that make sense?
Yeah, I get that. It's just
Good.
the
Okay,
oblique.
just give me a second. Where we can say it's okay now. This here is okay, we'll just continue, let's become also a transmitted wave. But let's say it's okay, his tissue bound here. Okay, and we still yes, okay, say yes, okay, it's still at a 90-degree angle. Now, in this case, yes, okay, if the impedance of this medium is equal to the impedance of this medium, then there will be no reflection. Did that make sense?
Yep.
Good. Now, if we say that, okay, yes, we have a tissue boundary, because it's okay, we have tissue boundary here. And let's say it's okay, we have an oblique incidence. Yeah, okay. So in this case, yes, okay, what we will have is there's going to be an incidence which is going to be oblique. Clear? Okay. Now, if we say that the impedances between these two media here are not the same, then, okay, yes, you will have a reflection. Did that make sense?
Yeah, I'm just confused because in the book,
Uh-huh.
that's not really what it's saying.
No. This is now, as far as what's going to happen to the transmitted wave, it may go on with no reflection. And that was in case that, okay, as the speeds were the same. So you can still have same speeds, but different impedances. Okay. Whereas a refraction is, okay, whichever degree is going to occur if the speed is not equal to the speed. Did that make sense?
Yeah, can I just read you one thing from the book that I think
Sure.
is throwing me off?
Okay, which page are you talking about here?
98 at the very bottom.
Okay,
It
98.
says, with oblique incidence, reflections may occur even when the impedance of the two media are identical. Furthermore, reflections may be absent even when the impedances are different. And then there's a chart on page 104
Mhm.
that says reflection with oblique incidence, we cannot predict, it's too complicated. So basically all I'm asking is, would you have to tell us, yes, it's reflecting?
Yeah, most likely.
So you'd have to say, okay,
Mhm,
this
mhm.
is an oblique incidence, it is reflecting, and then the question would be, what's the angle or what percent is like something like that. We wouldn't have to just straight up be like, yes, it's gonna reflect.
Yeah, yeah.
Okay, thank you.
But generally speaking, what you will have to remember is, okay, yes, that you have, it's going to be the difference in impedances that will lead to a reflection. Whether you had normal incidence or what do you call it, oblique incidences. Okay, the main thing that's going to, yes, okay, be different is that with an oblique incidence, well, okay, if you have difference in speeds, yes, okay, there will be refractions, which is going to be as okay that the transmitted wave is okay, don't continue on the same course or at the same angle, but actually it's okay, deviates.
Okay, so if the question said there's an oblique incidence, the impedances are different, we would say, yes, it's gonna reflect,
Mhm.
even
Reflect,
though that's not exactly what the book is saying, but that's the answer you're looking for.
very
Yes?
much.
Okay, thank you.
Anything else?
That's all from me.
Okay. Anybody else? Anybody else?
No.
Okay, guys. So let us just look at. Okay, done so far. So we talked of the matching layer. I think yesterday we had, okay, as a detailed account on the PCT crystals, active elements, whichever you want to go with. And yes, okay, though we just started, but we have talked a bit about, yes, okay, the backing material that we also could call the damping material. Okay, which we mainly say is okay that backing material is only going to be in what we call imaging transducers, or which are also going to be as okay your pulse wave transducers. Yeah, okay. Where on the other hand, we said, okay, yes, transducers without, or we can say, okay, with no backing material. That is going to be a continuous wave transducer, also known as a non-imaging transducer, or also known as a therapeutic transducer. Yeah, okay. And what we said that actually is okay caused transducers with backing material to be imaging transducer was that okay, yes, that it will actually is okay absorb. It will actually is okay absorb a lot of the vibrations from the crystals of the piezoelectrical material, and mainly cause that instead of having a continuous sound wave being produced, that it actually is okay due to the absorption, that it was going to just okay, just be a couple of cycles and then a pulse and then a break, and a couple of cycles, then break. Right? Did that make sense? So that's how it's okay. Due to the presence of backing material, that's okay. The transducer will be firing in pulses. Now, if it has backing material. Now, guys, all this, okay, your book says, okay, as what are other additional consequences related to the use of backing material. So backing material, or which also is okay called damping material. Okay, not it's okay. One thing that I was going to do is was going to just okay, we can just okay convert continuous waves into pulse waves. Another thing, three other consequences, as they call it, are going to be decreased sensitivity. Yeah, okay. So please keep in mind, guys, these are all as okay, going to be as okay due to the backing material. So what are these going to be? These are all going to be features of a pulsed wave transducer. That it will have decreased sensitivity. Now, guys, as far as the decreased sensitivity is concerned, we can actually say, okay, that is going to be as okay a negative effect or a negative consequence of having the backing material. Okay, what this decreased sensitivity means, we'll come to that in just a little bit. Other consequence of having a backing material is that we will have, okay, what we will refer to as a broad bandwidth. Clear? Okay. Some people may even ask, okay, change the word out broad by wide bandwidth. Yeah. And the third one is going to be as okay what we call a low quality factor. Now, a little odd name because, okay, this term here doesn't really have anything to do with quality. Clear? Okay. This quality factor here can also be referred to as the Q factor. Is that clear? Okay. So the consequences of having backing material in a transducer is going to be that, okay, yes, we will have a decreased sensitivity. We will have a broad or a wide bandwidth, which you can say is okay, would be the same as, okay, yes, great bandwidth. And we will have, yes, okay, a low, which is going to be, yes, okay, a decreased quality factor. Is that clear? Did you guys get that?
Yes.
Good. Now, we can then say that, let's put it this way, and it says, okay, consequences of no backing material. What will be the consequences of no backing material? And where will we see that? Those will be seen in a continuous wave transducer. And I hope you guys know that, okay, yes, it goes under other names as well. Okay, so let us put it this way. And if you said that, okay, yes, that if adding a backing material was going to cause a decreased or low sensitivity, then having no backing material, that's going to lead to a increased, or we can say, okay, a high sensitivity. Is that clear?
Yeah.
Good. On the other hand, if you said that, okay, yes, one of the consequences of having a backing material was going to, yes, okay, have a broad bandwidth or a wide bandwidth. You can mean it as, okay, not having a backing material that's going to lead to a less, or we can actually has, okay, is going to be referred to as a narrow bandwidth. Which mean that, okay, yes, we have a small bandwidth. Did that make sense? And the last but not the least, we can say is, okay, if the consequence of adding a backing material was that it was, okay, as a low quality factor or a low Q factor, not having a backing material, that is going to give us a great or a high quality factor or Q factor. Did that make sense? Just as it has said, well, okay, yes, these are the 4 points, or these are the topics that we will be talking about today. So what are going to be the consequences of attending the class? You get to know about those topics, right? Okay, you can say, okay, that'll be one consequence. Okay, the other consequence is that, okay, yes, I even gave out, okay, yes, a quiz guide to those of you who are here, right? Clear? Okay, and each of you get 10 bonus points in the next text. That's going to be the consequences of, yes, okay, being here in today's class. Now, if any of you tended to miss out what is it that is going to happen? Well, okay, yes, they will not be able to, yes, okay, participate in the discussion today. Clear? Okay. They will not be given the answer key. No, not answer key. Guide for the upcoming quiz. And they will not be given 10 bonus points. Did that make sense? Did that make any sense?
Yes.
So
Yeah.
having a
Yeah.
backing material, not having a backing material. Okay, so you know what the consequences of a backing material is? The opposite of those is just going to be not having a backing material. Did you guys get that? Good. Now, before we talk about increased or decreased, okay, before talking about yes, okay, increased or decreased, let us just yes, okay, get yes, okay, that cleared out. What do we mean by sensitivity?
The vibration of the PZT.
No, Krishna. But okay, listen here. Right now, I'm not talking in terms of ultrasound physics, just regularly. If you use the word sensitivity in a regular conversation with a lay person, what would the word sensitivity mean? Because once we got the meaning of the word cleared out, yes, okay, you know, well, it's going to be easy.
Fragile.
Okay, fragile.
Like easily bothered.
Easily bothered. Why? Because he or she is okay, senses it to a greater extent. So sensitivity just means the ability to sense. The word sensitivity just means the ability to sense. Clear? Okay. Now, some people may be so, you can say it's okay, sensitive, that if you just talk about, yes, okay, spiders and creeps and insects, they feel like, okay, yes, they are being attacked by those, right? Okay. Where, okay, some people may be so thick-skinned that, okay, yes, you can actually have, okay, yes, not just spiders and roaches and things like that walking around on them, but that's okay, that they actually won't feel it. So the person who is able to, as okay, sense weak stimuli is because he or she has a greater sensitivity. Where the opposite, that you is okay, a strong signal may not just okay trigger a feeling or trigger a just okay sensation, is because that person has a decreased sensitivity. Okay, and then you have people who are hypersensitive, which are allergics. Okay. Why do you call them why do you call it hypersensitivity? Because they react, or they actually overreact to certain things that normal, you shouldn't say normal, but that's okay, that other people would not have reacted to. Peanut butter, for instance, like who don't like peanut butter or peanuts, Okay. But then there are people who are actually going to just, okay, overreact just by the sight of peanuts. And that's mainly because they are too sensitive to whatever ingredient are content within the peanuts. Okay, whereas okay, otherwise there's okay, people with, you can say, okay, a normal sensitivity towards peanuts is going to be able to eat. Maybe it's okay, bags of you may get a stomach ache, but that's a different story. Right, okay. Okay. So sensitivity mainly is okay, just means that's okay, the ability to sense. And when you sense something, yes, okay, you're most likely going to react. Clear? Okay. A person with a normal sensitivity is okay, if he or she touches a hot stove, the reaction is going to be withdrawn. Clear? Okay. Where the person with a reduced sensitivity, he or she may touch that hot stove, but since he or she doesn't feel that that stove is hot, well, okay, yes, he maybe keep on keeping his or her hand on that hot stove, and actually, it's okay, may end up burning him or herself. Did that make sense? So when I said that your transducers, or let's say it's okay, the consequence of having yes, okay, a backing material, which was okay, a decreased sensitivity, is actually, you can say it's okay, it is a negative effect. Negative, or we can say it's okay, it actually is okay, going to be as okay, one of the bad effects of having a backing material, because it's going to reduce the sensitivity of the transducer. So what it mainly will mean to have a decreased or reduced sensitivity is that it will only respond to high intensity reflections. Okay, whereas low intensity reflections. Okay, why? Yes, okay. Okay. Since the low sensitivity will not be able to, because it's okay, stimulate the, or let's say it's okay, stimulate, be detected by the transducer. Okay, so we can mainly say okay. So mainly, and as a result of that, it's okay, very, very weak intensity reflections may not end up as okay, produce or have an as okay, appear on our images. Okay, so weak intensity reflections, that's okay, since of the decreased sensitivity due to the backing materials, okay, may not appear on our scans. Did that make sense? Because it's only going to be, yes, okay, responding to high intensity reflections. Did that make sense? So for some part, okay, you can say it's okay. Due to that, yes, okay, that's why, okay, it's decreased sensitivity caused by, yes, okay, having backing material in the transducer is going to be, yes, okay, a slightly negative point. Clear? Okay. But, what we will have is, yes, okay, we have our means of actually, yes, okay, counter that, which we'll talk about in a later chapter. Did you guys get that? Okay. Whereas, okay, is in a continuous wave transducer, which doesn't have backing material, what's going to be, as okay, the consequence of not having a backing material, increased sensitivity. Okay. So those strong reflections, as okay, will respond as okay, only, but as okay, since it has a lower sensitivity, or as okay, greater sensitivity, it will be able to, as okay, respond to weak intensity reflections. Right, okay. Greater sensitivity. Yes, okay, you will, of course, you will respond to, yes, okay, a strong stimulus. But mainly because of a greater sensitivity, a greater ability to sense, you will also be able to, yes, okay, feel. And of course, it's okay, you feel something or you see something, that's okay, you'll be able to, or you will respond to that. Did that make any sense? Or not? If you're blind, would you be able to sense that a lion walked into the room that you're sitting in? If you can't see,
You don't have to see, but you can hear and you can
okay, it's
feel.
a very clever line. He know that, okay, yes, I'm not going to make any sound because the person in this room here is only blind, he is not deaf. So if I roar, yes, okay, of course. Okay, unless, yes, okay, you are blind and deaf. Okay, and if you are that, then you are doomed. Okay. But let's just say it's okay that your visual acuity, as we call it, is reduced. You may only be able to see things that are at a certain distance or clear at a certain distance. So would you be able to sense that that line entered the room? No. Not unless, yes, okay, you have that feeling where you just go and see, well, I don't see anything, I don't hear anything, but I just know because I can just feel that there is, okay, there's something here in the room as well, right? Did that make sense? Okay, there may not be nothing wrong with your hearing. There may not be anything wrong with your, let's say, listening, smelling, so on, so on, so on, so. Okay. But you just feel something. That's because of, okay, as of an increased sensitivity. You have this sixth sense, call it, right? Okay. Okay. That just gives you, yes, okay, that feeling. Or some people will say, yes, okay, I can just feel it in the ear. Well, there's nothing in the ear. There's no smell. There's no change in temperature. There's nothing. So what the blue is it that you feel in the ear? Did that make sense? So that says, okay, increase sensitivity. Clear? Okay. And if you feel something or if you sense something, yes, okay, what is going to be, yes, okay. the normal human response. Or you can say, it's okay, okay, you're going to react to it. Or you can say, you're going to act upon it, okay? Of course, that's okay. If you are able to see a lion walking into your room, what will be your first reaction?
Run.
Okay. Do you think you're going to be able to run away from a lion? They may not be the fastest runners, but just okay, they can jump. So, okay. Let's not hope that there's a lion on loose. Okay, but that's your sensitivity. Okay. Any questions, guys? That's okay. As I said, this is slightly as okay a negative point of having a transducer. Sorry, having a backing material in a transducer. Okay, because what it causes is that okay, as it causes that this transducer is going to be less sensitive, which means that it will not respond to low intensity reflections. Clear? Okay. And if it doesn't respond to that, that may mean that okay, yes, they may not show up on the scan. But we have yes, okay, our means and ways of how to deal with that. Clear? Okay. But we'll talk about that in a later chapter. So for now, just remember packing material, consequence number one, low sensitivity. Okay. Now you don't have to remember it in this order. I'm not going to say what is the first consequence. What's the first consequence of having a packing material? And if you write low quality factor, and it's going to be wrong. No. Okay. These are not numbered in that way. Okay. Good. Any questions about sensitivity? Nope. Good. Then we can just get on to our next one, which is going to be as okay, wide bandwidth. Okay, now what I said about wide bandwidth, well, okay, yes, we can do it this way. And we say, oops. If we have backing material that is going to lead to, yes, okay, what we call a wide. We can also call it a broad. Okay. Or we can call it, yes, okay, a great bandwidth. Does that make sense? Whereas on the other hand, if we said that, okay, yes, we had no backing material, that was just going to lead to the opposite, which we're going to, okay, we'll just call a narrow. Okay, which you may as okay, just take as okay, the opposites of wide and broad. Or we can say as okay, or a low bandwidth. Did you guys get that? Yeah, okay. Where do we have the pink? Well, of course, okay, pink is going to be as okay what we see in pulse wave transducers. Where do we have the green? It's going to be as okay in a continuous wave transducer. Okay. But since right now, yes, okay, we are talking about, yes, okay, the actual consequence of backing materials, okay, we'll be sticking on to this one here. Did that make sense?
Yes.
Okay, guys. So just give me 2 minutes. I'll be right back. Okay. Thank you. Okay, guys. Thank you. Okay. So where were we? So the first thing that we need to talk about is what do we mean by the bandwidth? Yeah, okay. Yeah, okay. Now somebody may flip it around and say, okay, that's going to be the width of the band. Okay. Now guys, bandwidth here is okay, mainly has to do with, we can say it's okay, the range of frequencies. Is that clear? So that's pretty much okay as what a bandwidth is. It's going to be as okay, the range of frequencies. Now, guys, another thing, when you see the word range, yeah, okay. When you see the word range of anything, that means that's okay, just being that's okay. What's going to be the range? Which means that's okay, comes between, yes, okay, which is between the minimum and the maximum. Did you guys get that?
Yes.
Good. So what would that mainly mean that your bandwidth here is going to be? The bandwidth is just going to be as okay. Right now, we're not talking about large or small. We're just generally talking, okay, it's going to be as okay. It's going to be the range between your minimum frequency and let's say it's okay, the maximum frequency of your transducer. Did that make sense? So that's going to be the bandwidth. Now, what do you mean if you say that you have a wide bandwidth or a broad bandwidth, or let's say it's okay, a great bandwidth? That's mainly as okay. That's going to mean that you have a great range between the minimum and maximum frequency. Which mainly we know is when you say it's okay, a great range, that will mainly mean that there's going to be it's okay, a great difference between the two. Between your great minimum frequency and maximum frequency of the transducer. Is that clear? right? Okay. Whereas on the other hand, we can say it's okay, then what would be a narrow range or a narrow bandwidth? That's mainly going to be as okay if you have a lesser range, or as okay between the minimum and maximum frequency, or a lesser difference between the two. Now let's say it's okay, an example of a great bandwidth would have been that okay, we said that okay, as our minimum frequency was, let's say it's okay, 20 is probably 2 megahertz, and we said that the maximum frequency was 20 megahertz. In this case, here we can mainly say, okay, that the difference between these two, or the range between these two is okay, it extends from 2 to 8 to 20. So the range is going to be as okay, frequency of 18 megahertz. This is going to be our bandwidth. Whereas on the other hand, we can say it's okay, if we had a transducer where that's going to be as okay, a lesser range or a lesser bandwidth, we can say it's okay because this was still 2 megahertz. But then we can say it's okay, the maximum frequency was just 3 megahertz. So what is the difference between these two here? Is okay, the main is okay, just have a difference of just 1 megahertz, which will mean says okay, would be a lower difference between the maximum and minimum, which may mean that okay, yes, that will cause we will have a lower bandwidth. Did you guys get that?
Yes.
Good. So, as per standard, what a transducer with backing material will have. It will have a wide bandwidth. We can also say that would be as okay, a broad bandwidth, or as okay, that would be a great bandwidth. But what did we mean by the bandwidth? Was mainly as okay, just the range between minimum and maximum frequencies. Or we can say, okay, the difference between the minimum and maximum frequencies of the transducer. Now that difference would be broad, wide, or great, and that will give us okay, as what we'll call as okay, yeah, great bandwidth. Whereas on the other hand, if that difference is less, okay, because there's a lesser difference between the minimum frequency and the maximum frequency, that will give you, yes, okay, lesser bandwidth or a narrower bandwidth. Okay, so one thing is that's okay, whenever you see the range, right? Okay, whenever you see the word range, one thing that should come to your mind is that okay, that's going to be as okay, just what lies between two limits. You can say it's okay, the speed limits on the highway, for instance. Okay. Now, what do they mainly say is okay? 45 to 55. Okay, so that 10-mile range within, yes, okay, that you have to stay on. Clear, okay? But 45, that's the minimum that you can go with. 55 is the maximum. Clear? Okay, so that's the normal range of, let's say, it's okay, speeds on the highway. You go to local streets, that's okay, maybe even lesser because that's okay, 15 to 25. But you still have okay a range of 10 miles. Clear? Okay, although the range, or as okay, you can say okay, the speeds are the same. Okay, so you can put it this way and say, okay, the bandwidth. You can say speeds as bandwidths here, right? Okay, okay, you can say, okay, well, the bandwidth of range of speeds on highway versus the range of speeds on a local street was the same. Because in both cases, okay, there was a difference, okay, difference of 10 miles. On a highway, although it's okay, the range was from 50 or 45 to 55. But you can say on a local street, it was from 15 to 25. Did that make sense? Hello, guys. I get a froze all of a sudden, right?
Yeah.
Okay. So at what bandwidth? What was the last word that you hear coming out of my mouth?
You asked if we got it. We said yes.
Now, whoever is talking, you are freezing. Okay, I don't know why. My internet looks good. Okay. Okay, dear. You can't hear me?
No, he can't. You just asked if we understood and we said yes.
OMG. Okay. Can you hear me now?
Yes.
Yes, guys. Can you guys hear me?
You unfreeze for like a second and then you freeze again whenever we go to answer you.
Okay, Teresa can hear me.
Yes, we can all hear you.
Okay. Well, you guys just look frozen.
We keep answering, but then you refreeze.
Okay.
And we can hear each other, so I think it's on your end.
Okay, so what have you guys been saying then?
We've been answering what you've been asking us.
Okay, I did. Okay, now I can hear you guys. Okay. And you guys are moving as well. Otherwise, that's okay. Well, okay. Okay, guys. So what I mainly said was that if we keep, yes, okay, those speed limits, just to compare, okay, to something that we can relate to, right? Okay. The range of the minimum and maximum speed on a local street and the range of the minimum and maximum speed on a highway was the same because there was a difference of 10 miles between maximum and minimum on the highway from 45 to 55. Okay. But likewise, also a similar range or difference between the minimum and maximum speed on a local street. If we say that, okay, as minimum is 15 miles, maximum is 25 miles. Did that make sense? So that's what you mean by a range. Okay, okay. Although, yes, okay, the speed limits were different, but the range was the same. Did that make sense? So whenever you see the word range, what is the first thing that should come to your mind? That is always going to be as okay, a beginning value and an ending value. Okay, okay. Just like, okay, as for blood sugar, just for like, okay, blood pressures and things like that, they'll say, this is the normal range. We don't want you to go above that. We don't want you to get below that, because that's going to be diabetic, and that is going to be, as okay, hypoglycemic, for instance. Likewise for blood pressure, okay? This is the normal range. We want your blood pressure to stay in within these values here. Did that make sense? If you go above that, you become hypertensive. You go below that, you become hypotensive. But this is the range. Clear? Okay. So whenever you see a word range, that's okay. You say, okay, yes, that will mean what it means. Or that's mean is okay, what you should think. Okay. Did that make sense? Okay. So the range, or the difference between the maximum and minimum frequency of the transducer, that's what will be called a bandwidth. Clear? Okay. There will be a bandwidth. And for your pulsed wave transducers, due to the backing material, you will have a broadband, which will mainly mean that there's going to be a great range between the minimum frequency and the maximum frequency of your pulse. Did you guys get that? Whereas the opposite is going to be as okay what you have in a non-imaging transducer or a continuous wave transducer, because that doesn't have a backing material, so that will have a narrow range. A narrow range that we can say is okay, a smaller difference between the minimum and maximum frequencies. Clear? Okay, and that narrow range is just going to, or that range is just going to be a bandwidth, which is going to be narrow or small. Did you guys get that? Okay. Now in all this, yes, okay, there may be, yes, okay, two words or two terms that you also may come across. So we can say, yes, okay, let's do it this way. We said, okay, we have a transducer. We said, okay, it had a minimum frequency. Clear? Okay. Let's just say it's okay, 2 megahertz. Clear? Okay. We can say it's okay, we have a maximum frequency. Let's just say it's okay, 22 megahertz. Did that make sense? Clear? Okay. Now, this range, where we count from 12 to 22, that is going to be our bandwidth, which is mainly as okay. We can mainly say, okay, how do we calculate that? We mainly as okay, just subtract 2 from 22. And then gives us, okay, as a bandwidth of 20 megahertz. Is that clear? Did you guys get that?
Yep.
Good. Now, guys, when you go to the lab and you pick up a if you pick up a transducer, there's going to be a number written on that transducer. Most transducers will have a number written on it. 15, 7, 8, 20, whatsoever. And you may say, what the does this number here mean? Okay. Now that number is going to be as okay, what we mainly can call, or as okay, mainly what we're referring to as get the hell out. Main frequency. Clear? Okay. Now, please, guys, this term main frequency here can also be referred to as a resonant frequency. Is that clear?
Yes.
Good. So main frequency can also be referred to as a resonant frequency. And okay, guys, please don't. Okay, it doesn't necessarily have to be in the middle, in between. Yes, okay, exactly in between the frequencies of your bandwidth. But we can just say it's okay, just for this case, it's okay, so it's okay, our main frequency is 12 megahertz. Okay. So that's the main frequency of the transducer. Or yes, okay, what we call the resonant frequency of the transducer. But here, yes, okay, this transducer with a 12 megahertz frequency, in this case, we can say, okay, had a bandwidth of 20 megahertz, which we just can say is okay, just for comparison, we will say it's okay, that's going to be, it's okay, a great bandwidth. Did that make sense? Where on the other hand, we can still have, okay, yes, a transducer which has a main frequency, also known as a resonant frequency of 12 megahertz. But let's just say that, okay, in this instance here, it's okay, his minimum frequency is 10 megahertz. And the maximum frequency, for instance, okay, just was 14 megahertz. So although, yes, okay, it still has a main frequency of 12 megahertz, but if you look here, yes, okay, what is it that he or she is going to be having? Either there's going to be, yes, okay, a bandwidth, which is just going to be the difference between 10 and 12, 14, which is going to be 4 megahertz. Okay, where we mean is just, okay, this here will have a narrower bandwidth. Did you guys get that?
Yes.
Good. Okay. And higher bandwidth is mainly as, okay, something that we find in what we will call pulsed wave transducer, whereas, okay, as narrow bandwidth is going to be as, okay, what we find in continuous wave transducers. Why does this have the broad bandwidth? Mainly as, okay, as a consequence of the backing material. Why does this here have a narrow bandwidth? Mainly is okay because of no backing material. Did you guys get that? Did you guys get bandwidth? Clear, okay. Or if not, does your car have a radio? Okay. Now let's just assume that the car or the radio that you have in your car is a broadband radio. What would that mean? Now, what does it mean to be a broadband radio?
Would it be like a wide range of channels? or
Okay,
stations?
that you'll be able to catch on that, right?
Yeah.
Why? You are right, my dear, but why?
Because broadband means like a wide.
Okay, you are able to tune into a broad band of frequencies, right? A wide variety of frequencies. Good. Well, how would you be able to, yes, okay, be able to listen to a wide array of radio stations? You don't know?
No.
Okay. Do you guys know what format or what form is it that radio stations transmit their transmissions? What do they use? Please don't say a studio where people are sitting and okay, having a mic and so and so. They transmit those signals out on a specific frequency, right? Did that make sense? So what actually happens when you tune into, yes, okay, FM 101, your radio receiver is now able to catch a specific frequency. And if yes, okay, FM 101, yes, okay, is transmitting its signals on those frequencies, that's how you'll be able to listen to it. So when the frequency that you have set on your radio matches with the frequency of the radio station, that's when you catch the frequency. Just like we say, okay, how was it that cells communicate with one another? Remember that? The first chapter in A&P. That key fits into that keyhole, right? But here's okay, you says, okay, the frequency that you try to catch matches to the frequency that is being transmitted. Right? But you can say, okay, that's a broadband radio because you are able to just, okay, tune into a great range of frequencies, which means you were able to just, okay, listen to multiple different Okay, now
You froze again.
I froze again.
Mhm.
So did you hear that I said about, okay, not being on the same bandwidth? No, because you were frozen at that time. So my thing is, yes, but I don't know. You guys look frozen to me because nobody's moving. Okay. Okay. But you can mainly say, okay, the reason that you'll be able to say, okay, tune in on multiple radio stations, not at the same time, one at a time. Otherwise, it's going to be a mess. Okay. Okay. That you tune in, are able to just, okay, tune in to just, okay, a great variety of radio stations because that radio has a broad bandwidth. Okay. Whereas if you go to the dollar store and buy a radio there, how much bandwidth are you going to get for $1? Pretty not pretty much. Clear? Okay. So that radio most likely is okay, will be a narrow bandwidth radio. But what would that mean? Well, okay, yes. There's going to be as okay, it will only be able to as okay tune into a limited amount of frequencies, right? Did that make sense? So you may only be able to tune into as okay FM 99, FM 100, FM 101, or FM 102, 103, and 104, and that's it. Did that make sense? Okay. But anywhere in between the maximum frequency and the minimum frequency, which makes up the bandwidth, is going to be the main frequency, which we will also, yes, okay, refer on to as the resonant frequency. Clear? Any questions?
No.
No? There were once two people who were, that's okay, probably not the sharpest tool in the drawer, who were sitting and talking to one another. And they were bragging about, yes, okay, how cold it used to be when they were young. So one of them says, okay, when I was young, it used to be so cold that, okay, whenever we were milking a cow, instead of getting milk, we would get ice cream. And then the other person would say, well, okay, that's nothing. When I used to be young, it used to be so cold that if I said something, those words were actually, as okay, freeze in the ear. So the other guy goes and says, so how did you guys communicate with one another? And he'll say, well, okay, that was easy because we just catch the ear, or because just catch the words from the ear, put it right next to the ear, lit a match, and once it melted, put it in. So looking at just like what the internet connection is like now today, that may be the way by which we will be is okay. I'm going to just okay communicate. Okay, okay, guys. Just take a short break. Look at your well, okay, decrease sensitivity. Look at your bandwidth. Look at your main frequency known as resonant frequency. And when we come back to that, we may just okay use our bandwidth and our main frequency and talk about the quality factor. Clear? Okay. So, well, okay. I see you guys back at 35. Is that fair? Okay, let's hope that the internet gets settled by then. Any questions about sensitivity? Good. Any questions about bandwidth? So you guys good on bandwidth? Any questions about what it means to be a main or resonant frequency? Good. Because the next thing that we will be talking about is going to be quality factor, which we also call Q factor. Okay. Now, what we said that we had is okay, as a consequence of backing material was going to be as okay, a low quality factor, a low Q factor. Okay. And some of you guys are going to say, but we don't want low quality, we want good quality, we want high quality. Okay. But this term here doesn't have anything to do with quality. Okay. Okay. So just saying yes, okay, having a low quality factor doesn't mean that we are going to have okay low quality images and so on, so on, so. Okay. Okay. Just like okay, yes, a few letters later, yes, okay, there's something called the X factor. What's X factor? Nobody heard of X factor?
Like the show?
It's a TV show, right? Okay, okay. Jen, have you been watching it?
Not recently, but I used to really like Magicians, so I watched the episodes with the Magicians on it.
Ah, okay. So you've been watching some of the programs.
Yeah.
Okay, good. Okay. Okay. So nobody have watched X Factor? I haven't. Maybe it's okay, just short clips here and there. It's okay that pops up on YouTube or Facebook. I don't know why. But anyways, okay. So what is the X Factor then? If they get the X Factor, are they going to be X'd out?
I just realized that I mixed up X Factor with America's Got Talent, so because they also do
Okay.
X's. Sorry, never mind.
They just renamed it?
No, it's two different shows, but they both do like X's when you're wrong, when they don't like you. So that's why I got
Okay.
confused.
So
X
you got
Factor is
crossed
singing.
out, right?
Yeah, X Factor is singing.
Okay. Well, same thing. America Got Talent, I guess, is just okay as a array of different things that you may display. Okay. Comedy, papa, pee pee, poo poo, that's okay. Anyways, but don't we have American Idol? So mainly it's okay, same kind of concept, just different programs, different hosts. Okay, peace be with that. Okay, good. So that's okay. If you have the X factor, then you're being X'd out. And that mainly means, okay, you don't have that. So, anyways, so quality factor here, well, quality has nothing to do with quality as we know it. Yeah, okay. So what in the blue is quality factor. Now, maybe that's okay because it's factor just like factor is going to be unitless. Yeah, okay, so it's not going to have any unit. It's not going to have a unit of centimeters per whatsoever or any unit. There's no unit for your quality factor. Okay. And actually, that's okay. It's something that's going to be calculated again. It's rather being calculated than measured. So what makes our Q factor? That's mainly as okay. There's going to be as okay what we call the main frequency. Now, please keep in mind, guys, as I said earlier, this main frequency here is okay, could also be referred to as the resonant frequency. Yeah, okay. But your main frequency, all your resonant frequency divided by your bandwidth. Did you guys get that?
Yeah.
Good. Now, what did we see that transducers with backing material had? Transducers with backing materials, okay, they had a great bandwidth. Clear? Okay. They have a great bandwidth. Okay. Whereas, okay, yes, whatever main frequency we had for the transducer, any number divided by a greater number is going to give you as okay a low result. So guys, based on this, and that's mainly as okay, the main relationship that you will need to as okay, keep in mind that Q factor is inversely proportional to bandwidth. Yeah, okay. That we said is okay because having a backing material, you're going to have okay, it's a great bandwidth. And due to that great bandwidth, a low quality factor. Whereas, okay, as in transducers where there's no backing material, it's just going to be the opposite. We had a low bandwidth, and due to that low bandwidth, yes, okay, we had a great quality factor. Okay, so what we see is a green that's going to be okay if there was no backing material. The reds is if we had backing material. Now earlier it's okay when we talked about these frequencies, or we can say it's okay, these transducers here. Clear, okay. Did that make sense? So what can we say is okay, now what was going to be is okay, let's just try to is okay. Calculate our Q factor here versus Q factor here. Now what did we say? We had a resonant frequency of 12 megahertz. Or a main frequency of 12 megahertz. But here it's okay, what did we have? We had a great bandwidth of 22 megahertz. Yeah, okay. Whereas over here, we had a bandwidth, or we had a main frequency of 12 megahertz, but it's okay, just a bandwidth of only 4 megahertz. Now here is straightforward. We can mainly says, okay, let's do it this way. And we can say, okay, our quality factor is going to be as okay. 4 divided by 3 or 4 is 3. So it's okay, here our quality factor is 3. Over here, it's okay, I might have that's okay, screwed up for myself, but we can mainly say it's okay. 12 divided by 22. Now you can't do that. So you can mean it's okay, this is okay. If you add a 0 and put a decimal. Okay. But it's going to be as okay, I guess. 80 something or 0.8 or something like that. But what we mean is okay, just can see here that okay, as due to as okay, a greater bandwidth, keeping it okay, the main frequency the same. We have a low quality factor. Where here we have a low bandwidth and we're going to have a great quality factor. Did you guys get that? Yeah, okay. And when talking of transducers, which transducers have a low high quality factor is in continuous wave transducers because of a narrow bandwidth, because of no backing material. And on the other hand, which has a low quality factor will be pulse wave transducers. Why? Because of a great bandwidth, because of backing material. Is that clear?
Yes.
So it's mainly as okay, just the relationship between Q factor and the bandwidth that you need to know. But it's okay, on top of that, it's okay, also it's okay to calculate your Q factor, which will be as okay, the main frequency. Also, it's okay, known as the resonant frequency, divided by the bandwidth. But of course, that's okay, you will have to know how to calculate the bandwidth, and that's mean it's okay, just it's okay, that the maximum frequency, you subtract the minimum frequency from that. That's going to give you a bandwidth. Did you guys get that? Did you guys get that?
Yes.
Yeah.
Any questions? Now the note on page 118. Okay, now just keep them in mind that, okay, yes, the shorter the pulse, the greater the bandwidth. The longer the pulse, the narrower the bandwidth. Lesser the bandwidth, sorry. Clear, okay. And if a pulse is non-stop, yes, okay, that becomes a continuous wave, right? Okay. But even that's okay if you take two pulses, even if you take two pulses, clear, okay, there you can say it's okay, one pulse had 3 cycles, one has 6 cycles. Clear, okay. Of course, that's okay. The one with 6 cycles in the pulse is going to be a longer pulse compared to that of a pulse with just 3 cycles. Now, provided that okay, the wavelength is the same, right? Okay. Did that make sense? Clear, okay. But then we may say, okay, the pulse which is shorter due to it's okay in this instance, okay, the less number of cycles is going to have a greater bandwidth than the longer pulse, which had 6 cycles. Is that clear? So that's just something that you just have to, you can say it's okay, memorize. Okay, there's no like way to just okay explain that concept. Okay. Unless you say it's okay, continuous pulse, which means it's okay, will just be as okay, a continuous wave, right? Okay, we'll have a narrower bandwidth. Or you can say it's okay, the narrowest bandwidth. So shorter pulse, greater bandwidth, longer pulse, narrower bandwidth. And a continuous wave, narrowest bandwidth. If you want to look at that way. Did you guys get that? Okay. So
Yeah.
what? Yes, Maria.
I was just saying, yes, got it.
Okay. So what determines that's okay? You can say the number of cycles in a pulse. That's going to be, it's okay, how absorbent is it that the backing material is? Let us put it that way. Clear? Okay. Where you can say, okay, what is going to determine the wavelength of each cycle that makes up that pulse? That is determined by the PCT, the thickness of the PCT. You remember that one? So those two together, as okay, makes up your spatial pulse length, which is directly proportional to your your spatial pulse length is directly proportional to what?
Wavelength.
Okay.
Pulse duration.
Pulse duration, because period and frequency or period and wavelength were directly proportional, right? Right? Did that make sense? But then on the other hand, you can say, okay, pulse duration is directly proportional to period, but will also be directly proportional to spatial pulse length, because period and wavelength were both directly proportional. Clear? Okay. But on the other hand, and we will see, and we will look at that in just a little bit, that the greater the wavelength, due to, yes, okay, greater thickness of the PCT, yes, okay, the lower will be the frequency. Because wavelength and frequency were or are and will be
Inversely related.
inversely related. Caitlin is getting this. Okay, dear. So guys, yes, okay, as far as the components of the transducer that we needed to talk about, yes, okay, that is over for now. Now, if you guys can revise all the things that I've been yapping about for the last 1.5 days, you should be good. If there's something which still doesn't fit in here, or you couldn't tune onto it because you are talking at different bandwidths, then ask me.
I just have one quick question.
Good.
So if going back to bandwidth,
Mhm.
so if we were have like on a quiz, it would tell us the frequency and then it would give us the range of the frequency too, right?
Well, okay, they may give you the bandwidth and say, well, okay, this is your bandwidth. Or if they ask you to, yes, okay, calculate the bandwidth, of course, yes, okay, they will give you, yes, okay, the maximum frequency, they will give you the minimum frequency.
Okay, that's what I needed to
Okay.
know. Thank you.
Because if I say, yes, okay, what's the range between
I
two
figured,
numbers, and I only give you one value, and so, but where's the upper range?
right.
If I give you the
Okay.
highest number, and you know, but where do you start from? Right, okay,
Yeah,
okay.
that's what I wanted to make sure.
Yeah, okay. But please be watchful because they may even, yes, okay, toss the number of main frequency into the question. Not using the wording make frequency, but yes, okay, resonant frequency. And of course, yes, okay, if you use that frequency to calculate your bandwidth, of course, yes, okay, you'll get down with a narrower bandwidth because what we said is okay that the main frequency or resonant frequency is okay falls somewhere, not necessarily in the middle between the two frequencies. Okay, that's not a must. Okay, but it's going to be as okay something in between those two maximum or minimum ranges, somewhere in between. But if you use the minimum, or if you use the main frequency and try to just okay calculate your bandwidth, you will get the wrong answer. And that wrong answer will be given as an option. And that meant that, okay, as either didn't you understand the question, or yes, okay, you didn't know how to do your math. Yep, okay. But no worries, that's okay. You will see, yes, okay, what kind of questions you can be asked about. Because what do we have on page 121? A list of 8 beautiful questions, right? Clear? Okay. Now, what I will be giving you guys is, should we say 10 minutes to try to answer these questions on your own, cover up the answers, and that's okay, see if they tally. Okay, when we come back, we can always, that's okay, go over them together. So I see you guys at 11:15. Yes, guys. Any questions? So, okay. Get so let's just briefly look at these questions here and see yes, okay, how they make any sense. Some of them may not, but peace be with that. Good. So we can say question number 1. And what we are given here is, okay, as you are given 5 substances. You're given backing material, you're given PCT, you're given matching layer, you're given gel, and help me Lord, they even gave you skin. Okay, whose impedances has been measured. Now, unfortunately, as okay, the labels identifying the impedances of each substance has fallen off these materials. These 5 labels are indicating impedances of 0.8 megaradians. Now we just can say as okay that we have different impedances. So we have as okay 0.8, 1.9, 1.6, 2, and this is a 2.0, and 1. Just we have it clear as okay 1.0. Okay. What are the impedances of soft tissue, matching layer, gel, skin, blah, 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 and so on, so on, so on. So maybe that's okay. You can maybe that's okay. Just go and see. Now, what did we know? That the higher its impedances was going to be for respectively as okay, matching layer. So impedances of is okay. This okay, go like this. Or let's see, it's okay, Rod. This will go here, and this will go here. Then we can say, okay, 1.6. That would be that a matching layer. 1 will be gel, and 0.8 will be skin. So the only thing that you need to know here is, okay, is that sequence. Then we know it's okay from PCT to matching layer, from matching layer to gel, from gel to skin. What happens is that there's going to be a decreasing in the impedance. Did that make sense? So that list at the bottom of, okay, which page that was? 116 is the answer for this question here. Did you guys get that?
Yep.
Good. Next one. So this is, okay, is pulse length. Now they're asking, is it directly or inversely related to pulse duration? Okay. Now, although, yes, okay, here they haven't said, okay, they didn't put the word spatial, but that's mainly, it's okay, what do we mean? So what did we just say before we went on break? Or even, yes, okay, have talked about in chapter 4. The spatial pulse length is directly proportional to pulse duration. Because here we have period, and here we have wavelength are directly proportional to one another. And in both instances, okay, they will be multiplied by a common factor, which was going to be the number of cycles. Number of cycles. Yeah, okay, so based on that sense, okay, this will be the same. But it's okay, you can say it's okay, a pulse with a cycle with a greater wavelength will have a greater period, which we'll call that, okay. Why are you doing this to me? Both of these here will be increased. Or on the other side, that if you have a lesser wavelength, we will have a shorter period, when we will call that we will have a less spatial pulse length, and okay, so a shorter pulse duration. Did that make sense? Clear?
Yes.
Good. Question number 3. And what they say here is, okay, the Q factor. Okay, and they're still asking us again, it's okay, is that directly or inversely related to your bandwidth? And I guess that's okay. We ended our previous discussion before break saying that, okay, yes, quality factor, or Q factor, as we also call it, is inversely proportional to the bandwidth. Which mainly mean that if you have a great bandwidth, you will have a low quality factor. Or vice versa. If you have a narrow bandwidth, you have a great quality factor. Okay, so that makes them both inversely related. Clear? Now our next question is pretty much okay, yes. A question in a similar way, but wait a minute, let's like that, okay, yes. Is pulse duration, is that either directly related or inversely related to bandwidth? And what I mainly said was that, okay, yes, if we had a pulse with a short pulse duration, that was going to have, okay, yes, a greater bandwidth. Whereas, okay, yes, on the other hand, if we had a pulse with a great pulse duration, we will have a low bandwidth. And if, for instance, okay, had continuous waves, that will have a very, very, very low bandwidth. Did that make sense? So here's okay, it was the red arrow is up and this red arrow here is down. That means these two fellows here are inversely related to one. Did that make sense?
Yep.
We can go on to our next question. So the sensitivity, that's question number 5. Okay. Sensitivity of the transducer that creates shorter pulse is likely to be greater than, later than, less than, or equal to. that of transducer creating a long pulse. So here we can say, okay, where you say, okay, pulse duration or spatial pulse length. Okay, you can say, okay, sensitivity. Of let's say it's okay, a pulse with a, let's say it's okay, that we take, for instance, just, that's going to be, let's say it's okay, equal to, less than, or greater than. It's a short pulse, okay, good. That these here are short. Is that going to be equal or the same as that of, okay, yes, transducer will actually had a great spatial, or had a greater pulse duration, and or is okay a greater spatial pulse length. Now, guys, you just have to look at, okay, as what is the effect of sensitivity. Now, where do we have this? Okay, because it's okay. It was a reduced sensitivity. That was because we had backing material. Whereas, okay, yes, which gave us pulses with shorter durations and shorter spatial pulse lengths. Clear? Okay. Whereas would it be the same to say that, okay, the sensitivity of this transducer here would be the same as the sensitivity of these transducers with low pulse duration and so on. So no, so they cannot be the same. Okay. So it's going to be as okay. Either does this here have a greater sensitivity or less sensitivity. Now, we know that, okay, as a transducer which has great pulse duration or great spatial pulse length is because it didn't have backing material. So this transducer here will have a greater sensitivity. So when relating this transducer sensitivity here to this transducer sensitivity, this here has a sensitivity which is less than what we have here. So that's your answer. So pulses are just okay, transducers with low pulse durations or shorter spatial pulse lengths, either or both, are going to have a less sensitivity than a transducer with great pulse duration or great spatial pulse length. That makes sense. Yeah, okay. Why? Because this one here has more backing material. This one here may have lesser backing material that produces longer pulses versus this one. But the may is okay, talk about the sensitivity. So less backing material increase the sensitivity. More backing material reduce the sensitivity. Okay, so that's okay. There was a little bit, that's okay. Holding your right ear or left ear with your left foot rather than it's okay with your left hand. Okay, a little bit is okay, twisting and turning around with the concepts. But did you guys get the idea? Okay, so not really anything you need to calculate. It's all about, it's okay, do you understand the relationships? Okay, but here's okay, they brought, okay, as you can see, a lot of just okay relationships into it. Any question, ladies and the gentlemen? No. Hey. Question number 6. All of the following all ticks, yes, okay, describes an imaging transducer except. So that's okay. We are mainly going to look for is okay, word expresses okay, yes, describes an imaging transducer. Now, please keep in mind this imaging transducer, oh, sorry, could also be referred to as a pulse wave transducer. Okay. Okay, so that word, yes, okay, imaging transducer can be replaced by a pulse wave transducer, but it will still be the same question. Okay, and what they were giving us here is okay, yes, 4 things. Now, 3 of them, yes, okay, will be specific or described as okay, features or characteristics of our imaging transducer. 1 of them is not, and it's the one that doesn't that you will have to answer with. Now, high sensitivity. You say it's okay, low Q factor. You say it's okay, wide bandwidth. And you say damped. Now, guys, what was a imaging transducer, a pulse wave transducer? Because again, transducer with backing material, or as we also can call it, okay, the damping material. So is a transducer with a damping material or backing material, is that going to have a high sensitivity? No, it's not. Rather, it was going to, yes, okay, have a low sensitivity. But a transducer with backing material is going to have, okay, yes, it will have a low band Q factor. It will have a wide bandwidth. And okay, yes, we can say, okay, the frequency of that is going to be damped. Or we can say, okay, it's going to be pulsed, which will be damped. Because our backing material, okay, was called damping material. Did you guys get that?
Yes.
Okay. Question number 7. True or false? Now, shorter duration events such as Dan pulses are more likely to be wide bandwidth. So this says, okay, it is correct to say that, okay, yes. Oh, that's it, okay. Shorter pulse duration. What that mainly mean that, okay, yes, it has a wide bandwidth. And again, yes, okay, guys, if you know that, okay, yes, a shorter pulse duration is due to backing material. Does backing material have provide us with a wide bandwidth? If both of these are true, that's true. Did that make sense?
Yes.
Good. And or yes, okay, you may say it's okay. You may be giving us okay pulses with 2 pulse durations. You can say it's okay. A great pulse duration. And let's say it's okay, a low pulse duration. If you don't like pulse duration, it's okay. You can go, it's okay with the spatial pulse now. It doesn't really matter. Okay, and then they may ask you, yes, okay, which of these two has a narrow bandwidth? Which of these two here will have a narrow bandwidth? A or B? Yes, guys.
A.
You go with A. And that's the right answer. So same concept can be asked in different ways. That's all I want to is okay. Now, what occurs when the PCT crystals temperature are elevated above the Curie point? Temperature above Curie point. Now, did you mind guys remember, yes, okay, what the Curie point was? We can say, okay, that was the temperature at which a piezoelectrical material polarized. Or if you don't want to say polarized, you can replace the word polarized by saying convert one form of energy into another form. Or if you don't like to say it that way either, you can say it's okay. Causes it to create a piezoelectric effect. Yeah. Well, what we said was that, okay, yes, if we expose our piezoelectrical materials to temperatures greater than the Curie point, it will depolarize, which may mean that it will not be able to convert one form of energy into another. Or it will not be able to create, or will not be able to create a piezoelectrical effect. So that's what we call depolarization. Or you can say, yes, okay, that transducer is finito. Finito mambadito. You guys get that. Good, but now, guys, or students, or what do you guys like to be called? What would you like me to address you as? Or what do you identify yourselves as?
I like students.
You like students?
Yeah.
Okay. So, okay, students. Okay, good. So, that was your transducers. That was the backing material, the piezoelectrical material, and the matching layer. Their thicknesses are related to the wavelength. Clear? Thickness. And it's okay with all that say it's okay for backing material. We talk about sensitivity, we talked about bandwidth, we talked about quality factor. Clear? Okay. When we talked bandwidth, in the middle of all that bandwidth we said that, okay, we had a main frequency, or what we also refer to as a resonant frequency. Did that make sense? Clear? Okay. Now, students, the question comes, or the question arises, how is it that this main frequency, not the bandwidth, this main frequency or resonant frequency of transducers are being determined? What's going to determine that? Yeah, okay. Now, when I say transducers, yes, okay, we are going to talk about how frequency are determined for two kind of transducers. And what are the two kind of transducers that we have come across so far? Continuous wave transducers versus pulse wave transducers. Is that clear? Good. So, okay, but here's, okay, what frequency is it that we are talking about? The main frequency or the resonant frequency? Okay, so yes, okay, how do we determine the main frequency? Also is okay known as the resonant frequency of transducers. As far as our transducers are concerned, we can say it's okay, we got two kind of transducers. The first one is going to be as okay, where it's okay called a continuous wave transducer. also known as a non-imaging transducer, or what we can call is a therapeutic transducer. Clear? Whereas the other fellow is going to be a pulsed wave transducer, which will also be as an imaging transducer. Now, what's going to be the main difference between these two here? This one here and again, yes, now strategically, I am just using the word damping material. And well, it doesn't really matter. We can say it's okay. It has damping material. Is that clear? Now, guys, although that's okay, you can say it's okay. These two transducers here may be hooked up to the same system, but their frequencies may not be the same. So why is it that there's going to be this difference here of the frequency? Now let's please, these are the main frequencies, not the bandwidths. Because that's okay. If you talk bandwidths, of course, that's okay. Those will not be the same either, because we know that this fellow here is going to have a low bandwidth, whereas this one is going to have a great bandwidth. But that was just the difference between the maximum and minimum frequencies. Clear? Okay. But here it's we're not talking about that. We mainly just just referring to yes, how do we determine the main frequency or the resonant frequency? Now, guys, for your continuous wave transducer, now, as I said yesterday, and strategically, it's just use the word here again, that it doesn't have any damping material. And what did we say that the damping material meant? Or the word damping?
To like cool down, slow down.
Cool down, slow down. Okay? And again, yes, guys. You can say it's okay. Since this transducer here doesn't have a material built into it that is going to just slow down or calm down, or you can say it's reduce the frequency at which it's the crystals are going to be vibrating. So the stronger, the more the frequent gushes of wind entering through that open door, likewise is it that going to be an equal shivering of the crystals of your chandelier that you have hanging in the main entrance, right? So what would that tell us? Or what should we get from that? That the frequency of your transducer, if it is a continuous wave transducer, that frequency of that transducer mainly because, okay, frequency here is going to be equal to the frequency of the electrical energy or signal, if you want to put it that way. So if the frequency of the electrical energy is okay produced by your system is 2000 megahertz, then that continuous wave transducer is also going to have a frequency which is going to be as okay 2000 megahertz. Probably that's okay a little bit extreme, but anyways. If the electrical signal of your system had a frequency of 20 megahertz, the frequency of your continuous wave transducer will also just have been 20 megahertz. So here is okay, guys or students, sorry, there is no hocus pocus, no ups and downs. Clear? The frequency of your electrical signal stimulates your PCTs or your crystals at a frequency which is going to be equal to that of the frequency of the system or electrical signal. So it's not going to get damped down. Okay? So if you can mainly put it this way and say, okay, he probably needs to get a walk. Okay. If I hand out 20 candies in a minute, and you who receive those 20 candies in a minute hand those 20 candies over to the next person in a minute, that's because you don't keep any of the candies for yourself. For me, it's okay saying that, okay, yes, if you receive 20 candies in a minute and you hand it over in those 20 candies in a minute, well, okay, yes, what you receive is equal to, yes, okay, what you produce or what you pass over. Because there was nothing built into you that's okay, let me keep 5 of those candies for myself. Did that make sense? Okay, but please, guys, and that's why it's okay, keep on repeating that a continuous wave transducer is a non-imaging transducer, is a therapeutic transducer. Okay, and as you will see after a break, pulsed wave transducer is a imaging transducer. Okay, but the way of, let's say, it's okay, determining the frequency of a pulse wave transducer is a little bit more, should I say, complex, so we have to look into as okay, some other things before getting to that. So there are going to be okay, some relationships here. What we relate the frequency to, yes, okay, we'll come back to that. Clear, okay? But it's mainly going to be as okay, something that will be as okay, mainly circulating around your PCT. PCT, piezoelectrical material, ferroelectrical material, or the crystals, the active elements, or whatever you call it. Okay, the nature of that is going to just determine, or determine a factor of the frequency of your transducers or positive wave transducers. Clear? Did you guys get that? So that's okay. How that works, what the relationships are, and what we call them. Yes, okay. That's something that we will take up once you guys return from your lunch. If not stolen by the Grinch. Have fun, guys. And should we say that I see you guys at 12:50? Is that fair enough? Okay, good. Have fun till then. Okay, guys, students. Oh, let's see. Good. Any questions? Okay. So, for a pulse wave transducer, it's okay. Determining the frequency is not going to be as simple as for a continuous wave transducer. So let's just look at pulsed wave transducers. Frequency. Right? Yeah, okay. Now what we already know, or as we had said, frequency is okay, determined by source. In this case, it's okay, source is still going to be the transducer. Okay. Now, what is going to be as okay the two factors or as okay characteristics of your transducer that will determine the frequency is going to as okay be related to your PCT. Okay, it's going to both be as okay related to your PCT. So there's going to be as okay some features of your PCT within the transducer that will determine the frequency. And the first one is going to be, we can say, okay, the speed of sound in the PCT or your piezoelectrical material. Did that make sense? Okay. So that's going to be as okay one of the factors. We can say as okay, how does that make sense? Well, okay, the piezoelectrical material, it is, well, okay, it's a material. It is a matter, it's going to be as okay, still a type of medium. Okay, although not a tissue, but since this is the matter, it's going to be as okay, making up okay as a type of medium, and different mediums have different propagation speeds. Did that make sense? So of course, that's okay when the sound wave travels through the, you can say the piezoelectrical material, which is a medium, is okay. That sound is going to have, okay, as a certain speed. And that speed is going to, as okay, be, strange enough, as okay, related to the frequency of your pulse wave transducers. Did you guys get that?
Yes.
Yep.
Another feature or characteristic of your piezoelectrical material that will determine the frequency of the transducer, which is going to be a pulse wave transducer, is going to be the thickness of the PCT. Yeah, okay. So we can mainly say that, okay, yes, the thickness of the PCT, which I hope that I have clarified what we mean by the thickness, is going to, as okay, play a role in determining the frequency of that transducer. Did you guys get that? Okay. Any questions so far? Good. Then we can see. Okay. So what we mainly as okay are just going to be left with is establishing the relationship of the frequency of pulse wave transducers to these two factors here. How is it going to be related to the speed of sound in the piezoelectrical material? And how is it going to be, as okay, be related to the thickness of your piezoelectrical material? Now, guys, we can say it's okay. The frequency of a pulsed wave transducer. Now, its relationship to, let's say, as okay, the speed of sound in PZT is going to be directly related. Did you guys get that? What would that mean? That pulsed wave transducer will be a high frequency wave transducer. If the sound or speed through the piezoelectrical material was high. Or vice versa. It's going to be as okay a low frequency pulse wave transducer if the speed of sound of the ultrasound or of the sound wave was low. Okay. Now, although as okay, piezoelectrical material is okay as what we call lead zirconate titanate. Okay, but what they say is that okay, as the normal range of speed, and that's what we mean is okay, the normal range of speed of sound in your PCT can range from anything between 4 to 6 millimeters per microsecond. Did you guys get that? So for instance, okay, we said that, okay, yes, the speed of sound in the PCT or crystals was 4 millimeters per microsecond. That was mainly, yes, okay, when comparing these two, yes, okay, what I given us a low frequency. Whereas, okay, on the other hand, if it was 6 millimeters per microsecond, the speed of sound through the PCC, yes, okay, that would have been a high frequency transducer. Clear? Okay. If that's okay, this here was the same for both. Did you guys get that?
Yes.
Okay. Now all are not necessarily as okay relevant, but as okay, what we may say is that okay, yes, or you can say it's okay that sound of speed in PCT, for instance, is equal to okay, approximately 4 times the speed of sound in soft tissues. Yeah, okay. But if you look at the range of the speed, we can say, okay, the lower the speed of sound in the active elements, the lesser will be the frequency of that transducer, and vice versa. The greater the speed, the greater will be the frequency of that transducer. Did you guys get that? Okay, so frequency of a pulse wave transducer is directly proportional to the speed of sound in the piezoelectrical material. Did you guys get that?
Yes.
Good. Now we come to the other fellow. And we can still say it's okay, but what we still will be relating to is okay, where is the pulsed wave transducers frequency? Because now here it's okay, that was going to be related to, yes, okay, the thickness of the PCT. Yeah. Okay. Now there are 2 ways. You can either, yes, okay, just do it directly. And say, okay, let me just, yes, okay, simply memorize the relationship. Clear, okay? But then on top of that, it's okay, you maybe, it's okay, ask questions where they will say, okay, so on, so on, so on. So which transducer would have the greater frequency or lesser frequency? Okay, so let me just give it to you guys as okay, the simple direct way first. And okay, as what the relationship between the frequency of a pulse wave transducer is going to be is okay when looking at the thickness of the PCT. Is going to be is okay that they will be inversely proportional. What would that mean? What do you get from that? That a frequency which is like a pulse wave transducer that has a high frequency, clear? Okay, which has a high frequency. Or when we say frequency as okay, what we mainly are referring to is going to be as okay, the resonant frequency or mean frequency. Clear? Okay. That is going, that's mainly going to be because it has that PCT has a smaller thickness, or we can mainly say, okay, that's going to be as okay, a thin PCT. Did that make sense? Yeah, okay, so if you say thin PCT versus thinner PCT, and you compare, okay, and refer it to, yes, okay, these to the thickness, you will say, okay, a thin PCT is going to have a less thickness, whereas the thinner PCT is going to have a even lesser thickness. Did that make sense?
Yep.
Right, okay. Okay, but here is okay, we mainly as okay, relate thickness of the PCT to the frequency and say, well, okay, they are inversely proportional. Or you can say, okay, the thinner the frequency, the thinner the PCT, the lesser is going to be its thickness. And then hence says, okay, the lesser the thickness, the greater the frequency. Yep. Whereas if you do it the other way around and say, yes, okay, that a pulse wave frequency is okay, a pulse wave transducer with a low frequency. That's mainly going to be because that transducer had a greater thickness. Or that transducer's PCT was thicker. Did that make sense?
Yes.
Good. And now says, okay, the greater the thickness, less thin. Okay, guys. Now, if somebody wants to say, but I still want to, yes, okay, make some sense out of this. So just look, guys, because what we said, I think yesterday, we said that, okay, yes, the thickness of PCT was equal to, what was it equal to? Yes, guys.
Half of the wavelength,
Who said that?
Lily.
Exactly, my dear. So what was it that we said? If we had a transducer in which we had a PCT with a great thickness, that was going to produce a sound wave with a greater wavelength. Clear? Okay. Where we could say, okay, if the PCT, for instance, okay, was two millimeters thick, then in this case, yes, okay, the wavelength would have been 4 millimeters, right? Did that make sense?
Yes.
Whereas, and we can just say it's okay this way. Whereas, okay, if our PCT was one millimeter thick, then it will produce a wavelength which was 2 millimeters. That makes sense. But what we mainly can see here that, okay, yes, the greater the wavelength, or sorry, the greater the wavelength is usually as, okay, a thicker PCT. The smaller the wavelength is due to a thinner PCT. Okay, so yes, okay, that mainly made that, okay, yes, if you look at it, that the thickness of the PCT is going to be directly proportional to the wavelength. If you want to put it that way, right? That the thickness of your PCT is directly proportional to the wavelength. And okay, what do we know that wavelength is, or how is wavelength related to frequency? Inversely proportional. Did you guys get that?
Yep.
Yeah, okay. And or we can even say that, okay, yes, between these two PCTs here is okay. This one here will be as, okay, the thicker PCT, whereas this fellow here is going to be the thinner PCT. So this thinner PCT here is, okay, will have a lower wavelength, but due to that, a high frequency. Did any of this make any sense at all?
Yes.
Okay. But again, yes, okay, as I said, when you have two factors, okay, two factors that determine something, yes, okay, you have to look at both of them. Clear? Okay, so just like, okay, yes, your speed relationship, a propagation speed relationship to density and stiffness. You recall what kind of questions we had back then, where they say, which will have the greatest speed of sound, right? Greater stiffness, less stiffness, higher density, lower densities, and things like that. So you have to look at both of them. Okay, okay. But if they give you a question where they says, okay, two transducers made, that's okay, PCT made out of the same material. Okay, what will be the factor that you get from that question is that, okay, since they say it's okay, same material, propagation speed will be the same. But where they say it's okay, one is 1 millimeter thick, the other one is 3 millimeters thick, which is going to have the higher frequency. There is going to be one that is thinner, that is going to have the higher frequency because thickness of PCT was inversely proportional to the frequency. Did that make sense?
Yes.
Anybody in doubt? Good. So, okay. Now at the bottom of your page 125. What do you see? A big horrible equation, right? Okay. Specifically, guys, you do not need to remember this equation here. But if you just look at it, the only horrible thing is that, okay, yes, the thickness of the PCT is doubled. Right, okay, to determine the frequency. Okay, the relationships, yes, okay, sound or speed in PCT, that's your numerator of the equation, right? Which is directly proportional to the factor that we want to calculate, which here was the frequency. Whereas, okay, yes, thickness of PCT, that's the denominator, which is going to be inversely proportional to the frequency. Just like Q factor equation, that's okay, was mean frequency divided by bandwidth. So bandwidth in the equation to calculate your Q factor, a quality factor, was the denominator, which makes it inversely proportional. Did that make sense? Okay, but as far, okay, this equation here is, okay, specifically is concerned, Hakuna Matata. But the relationship, yes, okay, you need to know. If you didn't get the relationship, then okay, yes, I don't know what we've been doing for the last half hour. Okay, so directly proportional to the propagation speed of sound, not in soft tissue, not in lungs, not in bones, not in this, not in that, but in the PCT itself, which is, of course, yes, okay, it's a material, so yes, okay, it is going to have its own propagation speed. Clear? Material is going to be, okay, some sort of medium. Here is a medium, although yes, okay, we don't see it, but yes, okay, it is made up of particles. So yes, together it becomes the matter. Here, any questions? So students, or we can say yes, okay. This was all that I could offer for chapter number 8. And this is the point of this. Okay, this is going to be okay, the chapter that will be included on your quiz. So if you haven't got it yet, your quiz is on the date or you have it, unless whatever crazy rainstorm, snowstorm, whatsoever is okay, maybe heading hits us. I hope not. But the chapters that we will have is chapter 6, water chapter, chapter 7, okay, and chapter 8. So that will be as okay, the 3 chapters that you will have on your next quiz. Good. So we just try to just okay, look at some of these questions here, just to get started. We can see if we can agree upon the answers. And if you don't, well, okay. Or if you still didn't get how and why, yes, girls, please make sure that you ask me, okay? Good. So we're on page 126. And it's going to be as okay, question number 1. Now I got the first 18 questions are true and false. So you're going to be given a statement, and the main yes, okay will just say yes, okay, is this statement here true, or is this statement here false? So the first one reads, the acoustic impedance of matching layer is approximately the same as the impedance of skin. And that's false. Yeah, okay. Although yes, okay, the impedance of okay, yes, your matching layer, okay, yes, that was less than that of PCT. Or yes, okay, even less than that of okay, yes, your vacuum material. Of course, that's okay, it is greater than that of skin, but they are not the same. Is that clear? Question number 2. Imaging transducers. Now, once you see the word imaging transducer, what could be another thing that should come to your mind is a pulse wave transducer. Okay, are usually of high than lower bandwidth. So these have a high bandwidth rather than low. That is true. Yeah. Okay. Now, please keep in mind, guys, that, okay, yes, oh, sorry. Had they switched the bandwidth and says, okay, you had a lower bandwidth rather than higher bandwidth, then it became false. Which mainly means that, okay, as what we mainly as, okay, ideally is, okay, C in imaging transducer or pulse wave transducer is a higher bandwidth than it having a lower bandwidth. Did you guys get that?
Yep.
Good. Whereas if it had said, it says, okay, non-imaging transducer, then this here would have become true. Although it's okay, that was false for your pulse wave transducers. Question number 3. Now, a very high Q factor transducer is used more often in diagnostic imaging transducer than low Q factor. So it's okay for diagnostic imaging. Now, when we say diagnostic imaging, that's mainly it's okay when we want to, it's okay, create an image. So if you want to, it's okay, get an image. Would it be true to say that we use transducers with a high Q factor rather than a low Q factor? No. So since no, that makes this statement here false. Okay, or you can mean it's okay, just as says, okay, imaging transducer, that's pulse wave transducer. Pulse wave transducer have backing material. So does backing material give you a high quality factor or a low quality factor? It gives you this. But while the question asks, does backing material give you a high quality factor? That's an answer no, or that's false. Did that make sense?
Yes.
Good. Okay. So you see, as okay, they don't necessarily use the word pulse wave transducer. They use some of those other terms. Now, question number 4. A pulse with a long pulse duration is likely to have a narrow bandwidth. So yes, okay. Great pulse duration. Now, please keep in mind that the pulse duration is okay. Could also have been is okay. Change down with by a great spatial pulse width. Okay. Why? Because it's okay. Both of these here is okay. Were directly proportional to one another. Okay. But mainly that's okay. What I say is okay. A pulse with a long pulse duration, is that going to have a low bandwidth? Yes. And since yes, then this statement is true. Did you guys get that?
Yes.
So that box on your yes, okay page regarding the bandwidth, yes, okay. Damping material in a transducer increases the sensitivity. Now, if you don't know that backing material, that's okay, also is known as damping material, that's okay, you are lost. Clear? Okay. And does backing material or damping materials, okay, lead to a increased sensitivity? The answer to that is no. And since the answer is no, that becomes false. Clear? Okay. The thing that backing material or damping material is okay may increase is the bandwidth. That's the only thing that will be increased by the backing material or damping material. Both sensitivity and Q factor are reduced as a result of your backing material. Where we says, okay, the reason that, okay, this is reduced because it is inverse to proportional to your bandwidth. Question 6. Damping material in a transducer increases the pulse length. And again, yes, okay, if you don't know that, okay, yes, your backing material was known as the damping materials, okay, you will again be lost. Although you might know that, okay, yes, backing material, damping materials, okay, actually lead to lower pulse durations, or we can say, okay, shorter pulses. Okay, but here they don't ask about the lower, but they actually say, does it increase the pulse duration or does it increase the pulse length? And that is not true. The answer to that is no. So yes, okay, it's no, then that becomes false. Yep. Likewise, in question 7, it's the same. Where again says, okay, using is okay, damping material. In a transducer, is okay, does that decrease the pulse duration? The answer to that is yes. And since the answer is yes, it's okay, that becomes true. Now, question number 8. Okay, and question number 9. Right now, it's okay, just skip those two, because those are talking about as okay resolutions. Lateral resolution is something that we will talk about in chapter number 10. Clear? Okay. Lateral resolution is going to be something that we talk about in chapter 10. Elevational resolution or longitudinal resolution we'll also talk about in chapter number 10. Clear? Okay. So these resolutions here is okay. We're going to be talking about them in chapter number 10. Clear? Okay. So question number 10. Not chapter number 10, question number 10. Okay, so 8 and 9, yes, okay, just skip those for now. Okay. So damping material in a transducer decreases the bandwidth. And that's again false, because what we know is that, okay, yes, for backing material also is okay in terms of, okay, this question known as backing or damping material is going to, yes, okay, increase the bandwidth and not decrease it. Okay, so since the question said, okay, decrease bandwidth, The answer to that is no, and that since it's no, yes, okay, this statement here is false. Okay, question number 11. Damping material in a transducer decreases the quality factor. Okay, does that lead to a decrease in the quality factor? The answer to this is yes. That transducers with backing material or damping material have a lower quality factor. So that becomes true. Did you guys get that?
Yep.
Question number 12. Now, if the frequency of electrical excitation of a pulse wave transducer is 6 megahertz, so we can say, okay, the electrical frequency is 6 megahertz. Well, what they smuggled in here is, okay, as for a pulse wave transducer. Then the operating frequency of the transducer is also 6 megahertz. That is false, or the answer to that is no. It would have been yes. Or we could say, okay, that would have been true had it not talked about a pulse wave transducer, but rather a continuous wave transducer, or a non-imaging transducer, or whatsoever. But when we talk about a pulse wave transducer, we can't say that the frequency of the electrical signal is going to be the same as the frequency of the continuous wave transducer. Did that make sense?
Yes.
Good. Question 13. Now, if the pulse repetition frequency of a transducer increased, then the frequency of the sound produced by the transducer will remain the same. So the media says, okay, if we increase the pulse repetition frequency, okay, sorry, that we increase the pulse repetition frequency, okay, of a transducer is the, and here's, okay, it is for a pulsed wave transducer. Okay. Okay, okay, so okay. Then the frequency of the transducer, so that frequency of the transducer going to be the same? Yes. And why is that? Mainly because pulse repetition frequency and the frequency of the transducers are not related. My question will be, how do we increase the pulse repetition frequency? Scooby-Doo, what do we do to increase the pulse repetition frequency? How would you increase the pulse repetition frequency?
Reduce the depth.
By reducing the depth. Very good, Jenny. Now, how do we reduce the depth? Do we make our screen smaller? How do we reduce the depth?
Adjust it on the machine.
Okay, how? Take a hammer and a sledgehammer and bang the screen from top to bottom, or what?
Turn the knob.
The knob. Here we go. We turn the knob, right? Did that make sense? But the frequency of your transducer will still remain the same. It's not that the frequency will increase or decrease. Right? Although it's okay, they are still, okay, these two kind of frequencies here are still unrelated. Okay, question 14, just skip that one as well. Because that's again, yes, okay, something that we will talk about in chapter 10. But you can say here, okay, now the trick point is that they say the diameter of the PCT. Clear? Okay, not the thickness. Clear? Okay. Okay. Now, what's going to determine your diameter? Let's just look at it. Why? Okay. If that's the case, okay, then we may end up skipping, okay, all of the questions. Now, if we find this as okay said that we had a PCT. Clear? Okay. Now here's okay, we can say, okay, this is the front side of the PCT. This is the back side of this PCT. So what does this dimension here become? Yes, ladies. Front to back of the PCT, what is this dimension going to be? Ladies, what is this dimension here?
Thickness?
Yeah, okay, so had is that thickness? Yes, okay, that would have determined the frequency. We could just say it's okay that they would have been inversely proportional. Whereas like, okay, guys, now what you will see later on is, okay, when we talk about PCT and we talk about its diameter, that diameter is going to be as, okay, either this or this. Where we then can say as, okay, this would be the height, or this will be the width. Is that clear? But neither of these two here is okay will determine the frequency of the PCT. Or that's like frequency of the transducer, sorry. But the thickness does. Okay?
I have a question.
Yes.
So the diameter isn't related to that?
Nope. Is not related to the frequency.
Okay, thank you.
Clear? Okay. What the diameter is going to be related to, yes, okay, we'll talk more about that in the next chapter. Did you guys get that?
Yeah.
And later on. But okay, then we mean yes, okay, we'll go and talk more specifically, yes, okay, related to height in some instances and related to width. Although here's okay, I made a PCT that we say, okay, it's like this. But most of our PCTs are going to be shaped like this. So what you will see is that, okay, yes, that their height is not going to be equal to the their width. Right? Okay. But yes, okay, they will still have, yes, okay, the same thickness. But what the thickness determines is the frequency. What the height is going to determine is going to be one kind of resolution. And that's why I said, okay, let's skip those resolution questions. What the width is going to determine, or the width of the PCT is going to determine, is going to be the another kind of resolution. Okay, where okay, yes, as a whole, yes, okay, the diameter is going to, yes, okay, play a role in something else, but not to determine the frequency. Did you get that? So here it's okay, it becomes false because it's a diameter. Had it said thickness, then of course, just okay, it would determine. Did you get that?
Yes.
Good. Question 15. If the frequency of electrical excitation voltage of a continuous wave transducer is 6 megahertz, then the operating frequency of the transducer is 6 megahertz. And it was the same 6 megahertz that we had in the previous question, where it says, okay, that this was going to be, it's okay, the electrical frequency. And it says, okay, is this going to be, it's okay, the frequency of the transducer? Yes, because the kind of transducer that we talked about here is a continuous wave transducer. Did that make sense? Did that make sense?
Yes.
Yeah.
Good. So the answer to this is yes, and then makes it true. Question 16. Now, two piezoelectric materials or crystals are made of the same material. So that's okay. We can say it's okay. PZT1, PZT2. Now, I mainly, as okay, mentioned this earlier, as okay, same material. And one of the factors that we get from same material is okay that the speeds in both of these materials here are going to be the same. Did that make sense? But what they then say is okay, as the thicker crystal makes a pulsed transducer with a higher frequency. So we can mainly say, okay, that one of these here will have a thicker PCT, where we can say, okay, this one here will have a thinner PCT. And would it be correct to say that, okay, this thicker PCT here has a higher frequency than this one? No, because thickness of PCT was inversely proportional to frequency. Which mainly mean that the thicker the PCT, the lower the frequency. So this thicker PCT cannot have a greater frequency of the two. It's rather going to be this one here that will have a greater frequency. So since it makes no for this, that becomes false. And they ask about it, okay, the transducer with a thinner PCT or a PCT of a lesser thickness had a higher frequency? Yes. Right. Did that make sense?
Yes.
Yeah.
Good. Question number 17. Now, two PCT crystals are made from the same material. So again, because it's okay, PCT1 versus PCT2, just to have something to look at. Okay, now again, as okay, we say, okay, same material. So that mainly means that, okay, as the speeds of the material, or the speeds here is going to be the same as well. Yeah, okay. Now the thicker PC or the thicker crystal will make a continuous wave transducer with a lower frequency. So just because we say, okay, let's say it's okay that this one here has a thicker PCT, and this one here is okay was a thinner PCT. Would this make it be as okay a transducer with a or a continuous wave transducer with a greater frequency? I'm sorry, even lower frequency, sorry. And guys, the reason that, okay, yes, this answer here is false because the statement to this is true. Is that, okay, yes, the frequency of your continuous wave transducer is not dependent upon the thickness of the PCT. This frequency here was going to be related to the electrical frequency. Did that make sense? So even as, okay, if we had two continuous wave transducers with same okay, material PCT, But when one PCT was thicker, the other one was thinner. But they were stimulated by the same electrical signal, that's okay. They will have the same frequency because they were both continuous wave transducers. Did that make sense? So if you don't look closely, yes, okay, at the first read, question 16 and question 17 may be the same, right? But the thing that, okay, yes, makes the answer is okay, well, okay, is the reason. Okay. Is that okay, yes? That in one they talk about, well, okay, first they talk about the higher frequency, and one another they talk about the lower frequency. But then in one they even talk about it's okay, it being a continuous wave transducer. So your continuous wave transducer, guys or ladies or students, is not going to be related to the thickness of this PCT or the speed of sound in that PCT. It is going to be related to the frequency of the electrical signal. Did that make sense? Because those PCT does not get damped. Calm down, cool down. The frequency of the wind blows is going to just okay cause the PCT to just okay shake or vibrate at the same frequency. Okay. And guys, students, please, please, please look at the thickness. Okay. Clear? Okay, so thickness is going to be different from width, and thickness is going to be different from height. Or we can say, it's okay, they're going to be related to different things. Okay. Okay, guys. God bless. And well, okay. Just try to remain, just okay. If you can't, that's okay. Answer the remaining questions. There's some questions that's okay in the back of the book. You'll find those under, it's okay, the heading transducers. Yeah, okay. Okay. But when they ask about resolutions, if they do so, yes, okay, just leave those aside. Okay. So we can see what tomorrow's day bring. What is it tomorrow? Thursday?
Yeah.
Okay, girls. Okay. Have fun till then. Stay dry, stay warm, and stay safe.
See you tomorrow.
Bye.
Okay, bye-bye, dear.